So far, we have introduced matrices as functions that are applied to input vectors. We argued that they take input vectors and they rotate them, and they give some other vectors, output vectors. And we argued that it is essential to understand that these are the functional and learnable parts in our neural networks. So far, we don't know what actually we have not yet discussed what actually um, these weight matrices or matrices for that matter uh, do and how they contribute to the estimation problem, the AI problem. But we have discussed that sometimes what they do is they take the vectors or all of the vectors in the original space and they warp the space in a way and they leave with some other space. Whether it is higher dimensional or lower dimensional, that's, we argued, it's decided by the number of rows in this matrix. Our matrices might not be always square, they can be rectangular matrices, and therefore these rectangular matrices are probably going to give us longer, higher dimensional output vectors or lower dimensional output vectors. At some point, we discussed that this matrix operation to a space, to a vector space, warps the space. And sometimes we argued that this warping does in fact collapse to a lower dimensional space, or sometimes it flips the space. Remember our discussion when we entered, when we discussed matrices um, starting from unit vectors, it can actually leave a parallelogram as you see here, or flip the space, or even collapse into a line. So this is important from two aspects. One, that we will sometimes want to come back from where our matrix projected us to. And sometimes, as you see in the third example, it is not going to be possible to come back. Once we're there is no coming back. So, and we argued what determines this thing, and the name comes from itself. Determinant determines actually what this matrix does to an input space. So determinant takes as input, determinant is a function that takes square matrices as input and gives you a scalar. So this scalar is going to tell you some information about what this square matrix does. Typical notation, either you can use determinant of A, det expression, or this vertical bars that we're accustomed to from absolute value in scalars. But for matrices, this operation shows determinant. How the determinant is calculated is for 2x2 matrices and 3x3 matrices are probably covered in simpler junior level linear algebra courses, but I will show you the basic animation that I prepared. What you do when you're calculating the determinant is that you take the diagonal and you take and multiply them minus the off diagonal. Here the diagonal is 1 times 3 and the off diagonal 2 times -2, and this determinant results in 7. When we go to 3x3 matrices, we make use of the adjugate operation. So what we do is we take, for 3x3 matrices, we take the first row, or any row for that matter, and the first column of the first row is going to be positive, hence the color green, and the second one is going to be negative, hence the color red, and the third one is going to be positive. So these scalars, we took the scalar, are going to be multiplied with some other scalars, but these scalars are going to be results of the results on some determinant of a smaller matrix within that big matrix. Which small matrix are we taking? We're taking the little matrix that is composed by taking the rows and the columns that's other than the row and column that we're talking about. So we take this one, right? So we calculate the determinant of this one. For the second one, the number 2, we take whatever remains, and for number 3, we take whatever remains. And since we know the 2 by 2 determinant calculation, all we have is just multiplying and adding numbers. And there we go, you have a determinant. So this determinant actually tells you that this matrix is not collapsing. The matrix is collapsing is if the determinant is 0. If it is greater than 0, it is actually warping the space. If it is greater than 1, it is expanding the space. If it is negative, it is flipping the space, for that matter. And just for fun, I included 4 by 4 determinant calculation, which you will never need. But just for the sake of completeness, it is the same story. We take the first row, positive, negative, and whatever remains from the first row, we take that and we attempt to calculate its determinant. And same thing for the second one, same thing for the third one, same thing for the fourth one. So now we have 4 3 by 3 determinant calculations multiplied with these numbers, and now the simulation gets even actually faster because we have already covered the process that was required. I apologize, sincerely apologize for that group that I'm in, and it's keeping me busy. I hope the recording doesn't show all of these WhatsApp notifications, but yeah, sorry, it is what it is. So we argued that matrices collapse, do something to their output, to their input, and we will want to come back from where we were projected. Sometimes it is not possible to come back from where we're projected, and other times, since it is a matrix that took me from where I started and landed, it is going to call for another matrix to take me from where I landed. So inverse of a matrix is defined, inverse of a matrix, inverses of matrices are defined for square matrices only, and it is defined like the inverse of multiplication in scalars with the to the negative 1 expression. And but this time, this to the negative 1 doesn't mean that you're going to take the multiplicative inverse of every single element of a matrix. Inverse of a matrix is another matrix that is going to undo this operation. Starting from week 2, we will look into how instrumental this inverse operations are going to be. Typically, you will use computer programs to calculate the inverse, but again, for the sake of completeness, the inverse is calculated similar to, borrowing some techniques that we learned from the determinant calculation, making use of the adjunct matrices, the small adjunct matrices. For example, in the slide you are seeing how the inverse of a 3 by 3 matrix is calculated. The inverse of a 3 by 3 A matrix is calculated by taking, for each and every one of the locations, creating a 3 by 3 matrix. For each and every one of the locations, notice that these are just determinants of the resulting adjunct matrices. What are adjunct matrices? Again, in the just like in the determinant calculation, we get whatever remains from closing up the row and the column of that particular index that we are interested in calculating, right? So we calculate 3 by 3 determinants, and there's another determinant here. We multiply this whole matrix with 1 over the determinant of the input matrix. Here is a part that I would like to stop and mention that notice how when you get a determinant of the input matrix to be 0, this division cannot be calculated, and therefore there's no coming back. So determinant 0 means that this matrix collapses you to a lower dimensional space or subspace, and there's no coming back. Such matrices have a name. We call such matrices singular matrices. Matrices with determinant is equal to 0 are called singular matrices, but we will cover this starting from week 2 again. And here in this animation, it shows you how the inverse is calculated. First thing that we do, since we know that since we're dealing with a 3 by 3 matrix, we create a 3 by 3 matrix. I'm interested in the first element, so I create its educate matrix and calculate its determinant and place it there. The second one, same way. I get whatever remains, put it there. Third one, same way. Don't worry, it's not going to be as slow. It's going to keep speeding up because you get the point, and we populate everything. Finally, we divide everything by 5, which is the determinant of the input matrix. So that was what matrix inverse, that was how matrix inverse is calculated.